So, good morning everybody and welcome to the next lecture in Bioprocess Engineering. Okay, third lecture, warm welcome. Before we start, maybe some, let's say, administrative points. Point one, lab course. Weil will make next week at Wednesday 2:30, to the best of my knowledge, a short introduction with respect to the lab course. Lab course will start in June, but just to keep you updated how the lab course will work. This will be, of course, announced in Moodle. All details you will see in Moodle. Second announcement is exam. The exam will not take part in the exam period of July. It will be in the exam period September, October, so the before winter semester exam period. Although I don't know yet how the exam will be, hopefully a written exam, but I cannot tell you at present. So, but it will not be exam period July. All examples in this section are based on the Bioprocess Engineering Principles, second edition, Academic Press from Pauline Duran. The solution path is also depicted in this book, so please refer to this book for details, and it's again a warm recommendation to have a look in this book. At present, we have talked about electron balances. You did not have a homework, but you hopefully remember that we talked about electron balances. Here we are. So that was a slide we have already seen last time. We have deduced the electron balance from this equation, and we have deduced this simple electron balances from this equation. And then you remember we have from this electron balance, we have rearranged it, and then we came up with the oxygen demand here. So this is our oxygen demand. We have just solved the equation to A, and then we have said the oxygen demand is simply our degree of reduction of our substrate fold a number of carbons minus the degree of reduction of our biomass fold the stoichiometric coefficient, and if there is a product, minus the degree of reduction of our product fold the number of carbons of our product. Here we are, fold the stoichiometric coefficient divided by 4. So the cool thing is, if you just need the oxygen demand, and that's the case especially in energy balances, then just using this equation you can solve the oxygen demand, and you don't need to know all other stoichiometric coefficients. You don't need to finalize a mass balance in this case. It makes life easier. So now let's have a look in what we can also do with this equation. So this is again the electron balance, and so the electron balance we said is annotated like this. We have our degree of reduction of the substrate minus 4a is equal to C, the degree of reduction of our biomass, plus the product. Okay, so at the end, the electron balance, what does it mean? So at the end, you would say that the amount of available electrons is always the same. So you can transfer the available electrons which come in from the substrate either to oxygen, to your biomass, or to your product. Although the oxygen stands here, at the end you transfer it because it's minus. So you could also write it like this. You could say the available electrons from our substrate, which is of course the degree of reduction fold the number of carbons, is equal to C degree of reduction biomass plus F degree of reduction product plus 4a. And now you can do the following. If you just divide now by the available electrons of the substrate, you will end up with this equation as CB divided by plus FJP divided by plus 4A divided by. In other words, the sum of the quotients where you have transferred your available electrons to must be 1 at the end. That's clear. You cannot bring in electrons in the system. But this equation now is quite helpful, because you say at a max, what is the maximum amount of electrons you can transfer? If you would have this term as 1, the other terms would be 0. Makes no more sense. So you just burn your biomass as your substrate and don't do anything else. But what you can do is, what happens if you transfer all electrons you have to your biomass? Well, in this case, this term will be 1, and this needs to be 0. So in other words, you come up with this equation: 1 is equal to C gamma B divided by omega gamma S. And in other words, this means C is equal to, and then it's just gamma S divided by degree of reduction of the biomass. And this C is not a normal C, this is the C max. So in other words, this is the thermodynamically maximal amount of biomass you can produce. That's clear. So if you transfer all electrons to your biomass, you produce as much biomass as you can. You cannot transfer more electrons to the biomass. So this term gives you the amount of biomass you could produce in the system without putting it to oxygen or something else. So that's a very useful term, because this helps you to decide whether in your production, whether you are close to what you can produce, you cannot get higher, or whether you are far away. So this is a very helpful term. And of course, this is a stoichiometric coefficient. So it makes, of course, sense to have that as a mass coefficient. So you can come in. You remember we have this equation YXS is equal to C for the molecular weight of the cells divided by the molecular weight of the substrate. I think this was our equation 25 or 20, if I'm correct. And then what you can do now is you can just substitute your C here, and then you can solve it. I will do it on one hand, so you can just try it. You will just put it in this equation, and then you solve it to YXS, and then you have your maximal biomass yield, and this is then of course gram per gram, and this is more helpful. We cells divided by gamma B degree of reduction of biomass fold MV substrate. Okay, so just going back, that I see you, that you see me. I don't see you, don't worry. So what does this mean? This means, in other words, that you now can calculate how much biomass at a maximum you can produce per gram of glucose. How many biomass can you produce? And this is calculated by using the degree of reduction. So what you need to do is simply calculate the degree of reduction of your substrate, calculate the degree of reduction of your biomass, and then just solve it, and that's it. Yeah. So this is, and of course you need to have the molecular weight. This is also something, and then you can go. So I would say we do that with an example. Let's switch back to the presentation. Oops, was not the wrong. So we solve that with an example. I put me here that you see the complete text. So here That's what we have calculated. That's what we have rearranged. So this is the maximum possible yield, the thermodynamic maximum possible yield. And let's do an example now. So the example is, what is the maximum possible yield for glucose if you use glucose as a substrate and with nitrogen as with ammonia as a nitrogen source. And we assume that the biomass has the following sum formula. Well, just go. So I want you now to try this calculation in parallel, and I will ask you for the result. So let's put the chat here, and we will go. Is the standard? It's a standard to name the variables in this way in order. Yeah, okay. So is it standard in this way or order? No, we only look at, remember, what we look at is just these 4 elements. We just look at carbon, we look at hydrogen, we look at oxygen and then nitrogen. So a substrate can have only these 4 elements. Yeah. So it's not getting more complicated. The formula will be more complicated, but we talk about stoichiometry. So a substrate can have these 4 elements in different composition. Our biomass can have these 4 elements in a different composition. Our product can have these elements in a different composition. So if we would have 2 products or so, we just add another term. So there is no change here. So this is in this case standard. Whether you name then your carbon with an omega for the substrate and A for an oxygen, at the end this doesn't matter. It might be that in another, I don't know, maybe there is a book who names it differently, but you don't care. At the end you come up with the same equation. So standard is the way that the equation is set up. I want to put my hand into fire that everyone uses the same notion for the naming here. That would go too far. Okay, so but now, why isn't the exam? I missed that. Why isn't the exam offered in July? Simply because in July we don't know yet how it will work, and most likely in July there will be no presence exam, and for bioprocess engineering this is difficult. That's the problem. So can you please show the formula? Formula? What formula? So what you should have at home if you sit at your computer, you should always have, this is a very important thing, always you should have a printout of your formulary next to you. So please do that, print it out, have it next to you, that you can always look it up, because you will be allowed to use that formulary also in the exam without handwritten notes, just the formulary. So get used to work with your formulary. That's very important. It has 18 pages. Always have your formulary next to you. So, but we go back. Oops. So the formulary for we want to calculate the maximum possible yield. That's our formula here. YXS is equal to this term here. So we need to calculate the degree of reduction of our substrate, the degree of reduction of our biomass, the molecular weight of our cells, and the molecular weight of our substrate. And that's what you need to do. And then you put that into this formula. So maybe I'd switch to another presentation. I go to this one here. So here is the formula. And now I just copy. So our biomass was CH 1.8, 0.5, N 0.2, and glucose is of course C6H12O6. So degree of reduction of our biomass is the question, degree of reduction of our substrate is the question, molecular weight of our biomass is the question, and molecular weight of our substrate is the question. So please tell me, I'm waiting for you. So you have all informations also here. So this is the biomass equation, CH 1.80, 0.5, N 0.2. Glucose is C6H12O6. And we have this equation, which at the end is the equation we're talking about. Or we can also use this equation, yeah, for the molar coefficient. So please tell me first the degree of reduction of the substrate and the molecular weight of the substrate, that I can add that. I'm waiting for you. So just put it in the chat, the responses. Oops. Is equal to, is equal to. The equal to I have already. Just give me the solution. And as these solutions are longer, then we will put that here. Oops. So, where are the solutions? I'm waiting for the solutions in the chat. While you are not allowed to provide solutions, only the students. So I'm asking for the degree of reduction of the substrate. The substrate is glucose. Formula is here. And the molecular weight of the substrate, which is I would say an easy question. Yeah? So hopefully not everybody's sleeping. So the formula, everything is here. Molecular weight of glucose is 180.16. That's very good. So we are here, we do the balancing and so on. So we're more engineers. So we are happy with carbon being 12 grams per mole, oxygen 16, hydrogen 1, and nitrogen 14. With these values, we are happy because that makes our life not too complicated. So the molecular weight of the substrate indeed is 180 grams per mole. And the molecular, the degree of reduction of our substrate is still missing. And the degree of reduction of our substrate. Yeah, perfect. So the degree of reduction of our substrate is 4. So you add the amount of available electrons is 6-fold 4 plus 12 minus 6-fold 2 divided by 6. And now let's come with the degree of reduction and the molecular weight of the biomass. So what is the molecular weight of the biomass? So I'm also waiting for the values. Please come up with the values here. And in parallel, you can of course also calculate the degree of reduction for the biomass. So it's for all of you sitting at the computer. Of course, I don't see you. You can also play Doom or whatsoever. However, it is for bioprocess engineering, the most important thing is do the calculations in parallel. Try also to solve yourself the things, because at the end, the exam is 80% calculation. So you need to be able to calculate things quickly, and you learn it by doing. And it's also during the lecture here. That's why we do this lecture also live. It's important to do the calculations. I could do it, of course, in a way that I'm just talking and showing it to you and calculating it. But this is not ideal. So we start with the biomass here. The molecular weight of the biomass, and you have calculated 24.6. That's better. So here I wouldn't put the commas too early. So 24.6 is almost good. So I know we have no ash here, so that's fine. Sorry, it's perfect. So the molecular weight of biomass is 24.6. It's simply 4 plus 1.8. No, sorry, biomass. It's 4. The carbons, it's 12. Sorry, let's do it like this. 12 plus 1.8 plus 0.5 fold 16 plus 0.2 fold 14. Oops. And we come up with 24.6. And the degree of reduction of our biomass is degree of reduction is 4.2 exactly. So the degree of reduction is 4.2. It's also correct. So we are here at 4. This is the carbon. Available electrons for our carbon plus 1.8 fold 1 is the degree of reduction of our hydrogen minus 0.5 fold 2 degree of reduction of oxygen. And the reference is ammonia. Therefore, it's minus 0.2 fold 3. And this is 4.2. Nothing to divide because it's already normalized to 1 carbon. So now things are very simple because we just need to put that in the equation. So we just need to go in this equation and we put everything here in. So we have our y xs max is equal to, so we put the amount of carbons in our glucose. This is 6 for the degree of reduction of our substrate, which is 4. For the molecular weight of our cells, which is where it is, 24.6, of course, gram per mole, by the way. I didn't put it here, so please just remember it should be there, 24.6 grams per mole divided by 4.2. This is the degree of reduction of our biomass, fold 180 grams per mole. This is the molecular weight of our substrate is equal to 1.78 grams per gram. So this is our result. In other words, from 1 gram glucose, I can produce 0.78 grams per grams biomass. And this is important that you, this is, you see, it's not 1, so you don't produce 1 gram. So this is, let's say if you look at it in a more naive way, one could think that if I bring in 1 gram glucose and I just produce biomass, I would expect to have 1 gram biomass coming out. No, you will produce water and so on. And that's the point. The transfer of electrons is here the correct thing. You can only produce 0.78 grams biomass per gram glucose. So you will not be able, however, with whatever optimization of your process, you will not be able to produce more. You can do the same for your substrate. If you for your product, if you want to see how much product could you produce, you can do the same using this equation. So that's very important that you understand that. So this is the maximum, the thermodynamic maximum possible yield for your biomass. Okay, now let's go back to the presentation. Hopefully we see the same result here. And yes, we see, oh, here we also calculate the carbon, the Cmax. So of course that's then the coefficient, the stoichiometric coefficient, which is 5.71. And what we can calculate is the carbon yield. That's also an interesting term here. So 5.71 is our stoichiometric coefficient directly coming off our electron balance. And then we can say if we divide it by the number of carbons, we say that 95% of our carbons go into our substrate at maximum. That's the carbon yield. Okay. Now we have the next example. So here we talk about, I'm not in the way now, this example is candidate utilis converts glucose to carbon dioxide and water during growth. That's not surprising. So the cell composition is like this, plus 5% ash. biomass is not just composed of carbon, hydrogen, oxygen, and nitrogen. So therefore we have also sulfur, phosphorus, and so on. And you put simply in this ash, because for your stoichiometric calculation this doesn't really matter. So you put that in the ash and everything is fine. So the molecular, in other words, the molecular weight is this sum plus 5% coming from the other elements. The yield of biomass from substrate is 0.5 grams per gram. So this is the YXS, the yield. We will talk about yield coefficients, by the way, later in the sections kinetics in more detail. Ammonia is used as the nitrogen source. Oxidation of glucose follows the following formula. This is, of course, something which I would not have to give to you. This is something you know by heart. This is just, if you burn glucose, you get out 6 molecules of carbon dioxide and 6 molecules of water if you burn 1 molecule of glucose. And now you want to know what the oxygen demand is with growth compared to that without. So with growth, you also produce here biomass. Without growth, you just produce here carbon dioxide and water. So what is the oxygen demand? And the next question is, Candida is also able to grow using ethanol as a substrate, producing cells of the same composition as above. On a mass basis, how do the maximum possible biomass yields for glucose and ethanol as substrate compare? We start here with the oxygen demand with growth compared to without. So we need to calculate the oxygen demand. And remember, to calculate the oxygen demand, where am I? Okay, to calculate the oxygen demand, we can simply use, again, it is ideal if you have now your printed out. Please print it out, because that's also what you use in the exam. Print it out. You're allowed to mark things in your formulary, but not to write anything in. You can mark it, you can put labels on and so on, but don't write anything in. So our oxygen demand is here. I flipped over it. Here's our oxygen demand. That's at the end what it's asked. So we have an equation with growth. Of course, we have no product formed in this case. So our oxygen demand is in this equation without the growth. And if we put this equation, we will see right away that we have two things. We have our oxygen demand and we have our stoichiometric coefficient C here. So we need to calculate the C, and if we have that and we have the degrees of reduction, then we can calculate the oxygen demand. This is a standard way how you get there. So this is something you should really remember. So let's go back to the exercise. Oops. So let's put first the things we had to the equation. So cell composition is CH 1.84. This is an H 1.84, O 0.55, N 0.2 plus 5% ash. And the yield of biomass from the substrate, and this is YXS, is equal to 0.5 grams per gram. Always put this grams per gram, because then you know it's a mass yield and not a molar yield. So a mass yield is given in grams per gram. I often give this stoichiometric coefficient C, for example, as mole per mole, in order that it's clear that it's stoichiometric. So that's all we have. So we go and first calculate in this case. Maybe I'll go to a screen where I can see the where I can see your comments already. So again, what you have to calculate is the molecular weight of the biomass, the degree of the reduction of the biomass, and the degree of reduction of your substrate we have already calculated from before. So it's glucose, so we can simply take the molecular weight of glucose from the exercise before. So we had 180 grams per mole, and we had the degree of reduction of glucose let's put glucose that it's clear, was, if I remember correctly, 4. No coefficients here. Of course, the degree of reduction and the biomass of our the molecular weight of our biomass we have to calculate again, because we have a different composition now. Yeah, growth doesn't refer to the product. Growth refers to the biomass. You will see it if we calculate it. So we have our in the equation before, what is given on the board. It's just glucose plus oxygen gives carbon dioxide plus water. But in our general equation without growth, we also have then, of course, a term for the biomass, because you grow the biomass. So you compare this chemical formula without the term of biomass with the term with biomass, and we calculate now the oxygen demand using our electron balance. But to do that, we first so you remember the equation is we have our equation for the oxygen demand. This is A is equal to degree of reduction of our substrate minus C-fold degree of reduction of biomass. The product is not formed here, divided by 4. So we need to know the degrees of reduction. So we need to calculate the degrees of reduction, and we need to calculate this. So this is therefore get used to the formulary. So that's how you approach also this this thing. So you can if you have this equation you have in the formulary. So you put this equation and you check on the equation, what do I actually need? And you say, okay, I need the degrees of reduction. This is straightforward to calculate, and I need this stoichiometric coefficient C. And then you go also to your formula, and then you realize, and C is that's also a term you have in your formula. C is equal to YXS fold molecular weight of your substrate divided by molecular weight of your biomass. Oh, this is something I can't read. Okay, and we have YXS is given. So YXS is here. And we just need to calculate also then this one. Oops, this is a bit too thick. I prefer the smaller one. We need to calculate this one and this one. Yeah. And then we have our C. And then we can put the C inside. So this is how you proceed. Put the values and then just look on what you have to calculate. Do we have to multiply the biomass with 1.05 because of the mesh? Because of the ash. We come to that point in a second when we do the calculation. You should not forget the ash. Yes. YXY when it's the yield of biomass. It's YXS. So maybe this is not here. This is not nicely written. I write it again here. Yeah? It's not YXY. It's YXS. XS. So X stands always for biomass, by the way. And Y stands for substrate. So therefore you have this YX is biomass per S, again a Y, sorry, per S substrate. So biomass substrate. Yeah, so that's where it comes from. I put that in a different color, and then you see it also in this. So let's assume this is X. Oh, didn't take it. Oops, back. Now hopefully X. So we have here now X and our substrate. Let's take this color S. So it's biomass per substrate. This is how you nominate these yield coefficients. So this is we will talk about yield coefficients later on. Yeah. Okay, so come on and calculate. So we need to know first, you see, all our molecular weights. For glucose, we have it. So we need to have our molecular weight of our biomass. And we need to calculate our molecular weight of our substrate. Yeah. So I do it now like this, that I just simply put this equation here. Oops, not the best. So wait a second. Okay, now it works. I just put it here that we have more space here. Okay, yep. Now back. Then I can show, yeah, cell composition. So that's what we need. Okay, so I'm waiting for the molecular weight of our biomass. Molecular weight biomass. And I'm waiting for the degree of reduction of our biomass. You can give me the number. Molecular weight of the biomass is 25.44. Almost. So it's 25.44 without ash. So without ash, 25.44 grams per mole. Always put the units, yeah, it's grams per mole. That's without ash, and that's correct. You just do it to the simple calculation, and the degree of reduction of your biomass is 4.14. That's also correct. So also very straightforward calculation. 4.14 is the degree of reduction of our biomass, and we come up with 26.71. I come up with 26.78. Use the formula. So I have MV biomass total fold 5% is my ash, or I can say fold 95% is the MV biomass without ash, biomass without ash. So we divide. This is the point. How you transfer it, just divide it. Yeah. So this means MVB ash is equal to MVB without ash divided by 0.95, and then you get your I get 26.78 grams per mole. In this case, it's wise, if you calculate in between, you shouldn't round too much in between. That's the point. Maybe also my calculation, I have rounded it wrong, but usually I do the calculation with Excel. Of course, this is not what you can do in the exam, and then you have no rounding errors in between. So for your calculation, also for the exam, don't, because you will see that in longer calculations, you have many steps in between. Don't do a too rigid rounding in between. Otherwise, your end result simply will not be correct. Okay, so we have now all information. So you have calculated it, and then we can now just simply put it in our equation here. So we can calculate. We have now our molecular weights, and we have the yield coefficient. So we can calculate C. So here we go. So C is equal to YXS. YXS is 0.5 grams per gram. It's here. So this is our YXS here. Then we multiply it with the molecular weight of our substrate. We have already taken it from the other exercise, 180 grams per mole. divided by our molecular weight of the biomass with ash is 26.78 grams per mole, and we end up with so if you put that in your formula, you end up with, I end up with 3.36. And you can also put here mole per mole, because you produce, this means that you produce 3.36 mole of biomass from 1 mole of glucose. 3.36 mole biomass per 1 mole of glucose. Of course, molarities in biomasses are just, it's for balancing. It's not 1 mole biomass, not really makes sense. So therefore, the molar value of a stoichiometric coefficient for biomass is not so interesting. But now at the end, don't forget, we want to calculate our oxygen demand. So now we have everything. We have our C, we have our molecular weights. We don't need any more because we just needed the molecular weights for calculating the C, and we have our degrees of reduction. So we just put in everything and calculate the A. A is equal to the degree of reduction of our the number of carbons in our glucose is 6, and then we had already calculated the degree of reduction of our glucose is 4, minus, now it comes C. C we have calculated being 3.36 mole per mole, fold degree of reduction of our biomass, it's 4.14 divided by 4, and we get 2.52 mole per mole. So this 2.52 mole per mole means that per mole of glucose we need 2.52 moles per oxygen to produce, if we produce biomass in this reaction. So this is a very straightforward thing. We have calculated how much biomass we produce just based on our yield, because this is an experimental value. We have measured that. And then our molecular weights, we have calculated them, and then we get how much biomass we get. And then we calculate, using this term, we calculate how much oxygen we need. So we need 2.52 mole per mole. Can you go over last calculation? You meant C. Okay, just in a second. So this means with growth we need 2.52 mole oxygen. Without growth, well, it's simple. It's directly in the equation. Without growth, we need 6 moles of oxygen. Yeah. So 6 moles of oxygen is required without growth, because this comes simply from this stoichiometric equation. Okay, can you go over the last calculation? Of course. Oh, so you can't see the C here because it's in the. I'm just trying to move that a bit, that the C is visible. Now the C is visible. Okay. So again, this calculation, C, this comes from this equation here. Yeah? So this is the equation. C is the, you see, C is equal to the yield coefficient biomass per substrate, this term, fold the molecular weight of our substrate, this term, fold divided by the molecular weight of our biomass, this term. So I simply now put in the value. So I don't do a real calculation. I just put in the value. So this is my YXS. I have it given. This has been given in the exercise. This is YXS here. Yeah. So this comes from here. I just put it in. Then this is my molecular weight of our substrate. This we have calculated before. This value here. Yeah. And this value here is our molecular weight of our biomass, and we have calculated it here. So this is, I just put these values in the formula, and then I type it in my pocket calculator, and I get this 3.36 mole per mole. And then I put this 3.36, this is my C, and this goes in here. And this is then my A. So that's straightforward. Yeah. So this is really a basic calculation you really need to know at midnight. You will see that this is very important, especially when it goes to energy balances. Yeah. Okay. Now we can do the same in the question. I will not do the calculation with all of you. You can try that at home. Now you can do the same with ethanol. Yeah. So the question was also, what is the maximum possible yield? And this is quite straightforward. So therefore we don't do that here as a calculation. So just going, I hope I have, I don't remember whether I have, yeah, the solution is here. That's good. So I can show you the solution. So this is what we have calculated. We have this 2.52. This is what we also got is our A. So of course we can calculate the percentage. 2.5 divided by 6. So that means that with growth we only need 42% of the oxygen compared to without growth. That's clear because some electrons go into the biomass and not into oxygen. You need less oxygen if you have a growth in contrast to without growth. Now the maximum possible yields, we calculate it the same way as we have done it before in this example. So we use this equation for the maximum possible yield with glucose, and we have also the equation with respect to the mass terms, and we use the degrees of reduction. We have calculated the degrees of reduction for glucose, so we get 5.8. Remember that the biomass now is a bit different. Before we had the biomass without ash in the first example. Now we have it with ash, so the biomass is 26.78 grams per mole, and we get a possible yield of 0.86. If we do the same with ethanol, we get a maximum possible biomass yield of 2.9. This looks like the yield with ethanol is smaller, but I would say this is clear because ethanol has less carbon, so there is less energy in a molecule of ethanol. So therefore the molar yield coefficients, of course, are important for your equation. However, the molar yield coefficients don't tell you directly something. So what you could do is normalize to carbons. And if you would do that, you would already see, oh, this is below 1 because you have 6 carbons here, and this is above 1 because you just have 2 carbons here. And it's even more evident if you go to mass terms, which is the more relevant, of course, calculation. So you produce 0.86 grams biomass from 1 gram glucose, but you produce 1.7 gram biomass from 1 gram ethanol. This is the maximum possible yield, thermodynamic. But of course, you can also translate that in real yields. And the translation into real yields is this one. This is why if your primary caloric input is beer, you produce this biomass with the beer. So that's what you have. So it's based on thermodynamics, unfortunately. So if you decide just to switch to beer, you have to live then with this value. Usually you don't develop that at an age of, so you're 20 to 25. Usually you develop that later on, but it will come, believe me. So this comes just out of the thermodynamics. And why? Because the degree of reduction of ethanol here is 6. The degree of reduction of glucose is 4. In other words, ethanol is more highly reduced. There are more electrons available, what you can transfer. And if you can transfer more electrons into biomass, you can produce more biomass. That's very simple. You have more energy. So the more reduced the substance is, the more energy the substance has. That's clear. So if you calculate then the heat of reactions in relation to oxygen, you can burn more because there is less oxygen in the molecule. The higher the degree of reduction, the more the energy. And the cool thing about the degree of reduction is the degree of reduction has already been normalized to carbon. So you can directly compare the degree of reduction with respect to the energy, not the available electrons, because that depends on how many carbons you have. So you see that the degree of reduction of ethanol is 50% higher than the degree of reduction of glucose. So you have 50% more energy in a molecule in ethanol compared to glucose. That's right the way. Okay, just looking at potential questions. I think this is what I have done, hopefully. Otherwise, I will just go back and show you again. Yeah, so this is with growth. It's simply using the complete equation. This comes from, because we have produced in the exercise, we have said that we have a yield of biomass from substrate 0.5 grams per gram. So there is growth in the normal reaction. And then, of course, this is not the term. It is, we come from this equation. Just kick away the product. So we have here a biomass term. We have here then glucose. We have plus oxygen gives biomass plus carbon dioxide plus water. And then we don't need to balance for the other stoichiometric coefficient. That's important. If we are just interested in the oxygen demand, of course, we also produce carbon dioxide and water here. We don't care about the stoichiometric coefficient. That's very important. If you just ask for the oxygen demand, you can go with your electron balance and then do it. It's way more complicated if you would first balance the complete equation. What is possible, but this takes way longer because you need to solve then a system. You need to set up and solve a system of linear equations. And why should you do it if you can put it in a very simple formulary? So that's the better way. You save a lot of time. Sometimes people in the exam, if they're asked for an oxygen demand, go via really solving the systems of linear equation, but then of course they lost due to a time problem, because then they exhausted all their time just for doing this calculation. Okay, so and therefore, you then, as we do it like this, we calculate the stoichiometric coefficient for C, calculate the oxygen demand, straightforward, and we get 2.52, and that's it. And without growth, you simply take this equation. Without growth, you say, if I use 1 molecule of glucose, I need 6 molecules of oxygen to completely oxidize it. So there we have the 6 directly. We don't have to calculate anything. That comes from this equation. And then it's just 2.5 divided by 6, and we end up with 42%. Okay. So now let's go on. We come to energy balances now. Oops, that was maybe a quick. So balancing bioprocesses, we have talked about material balances, we have talked about stoichiometric balances, we have talked about how valuable it is if you use the electron balances, and how cool it is if you just need the oxygen demand. And you will remember in energy balances, this is an anaerobic process. If you calculate then the heat which is being produced, you will see, wow, it's cool. We just need to look at the electrons transferred to oxygen, and that makes then life very easy. So this oxygen, calculating just the oxygen demand, will become your friend even more in energy balances. And you have seen it's such a simple equation. You don't need to do many things here. Okay, that's what you should know. And now here we go. Of course, energy balances, the basics is what you have learned in physical chemistry or physics or chemical reaction engineering. There is no difference. It would be not good if in bioprocess engineering the rules of thermodynamics are different. They aren't. They are the same. So the basics in all reactions where you have no growth of biomass are the same. So for us, the add-on is what happens if we have a biomass included, and what can we do? But let's nevertheless first start with the basics. So forms of energy, of course, we have kinetic energy, we have potential energy, and we have internal energy. And the energy is transferred via heat. So that's an energy flow because of temperature differences, via work. So this is shaft work, for example, work done by moving a part in your bioreactor. this is your impeller, which is stirring, or flow work to push matter into your system if you pump something in your system. The enthalpy, of course, here we are at the internal energy. The enthalpy is the combination of our internal energy and flow work. And then we have our enthalpy, which is equal to the internal energy plus pressure volume. And we have our specific enthalpy, which is just per grams per whatever. Yeah, specific enthalpy, specific internal energy, and specific volumes. The point with enthalpies and internal energies, you know that from thermodynamics, you can neither measure it or know it. Therefore, absolute enthalpies you cannot assess. And of course, how can it look like now if we set up a system? This, of course, I could draw on a board, but I think that you believe me that it's clear at the end. If you look what happens in a system. You have a mass flow coming in, so we don't talk about bioprocesses. You have your substrate, for example, being fed into the system, and then you pump something out, for example, your biomass and your product. So you have a mass flow in the system, but for energy balances, of course, we have, in addition to the mass flows, where we bring in energy. So mass flows bring in energy due to the internal energy and the enthalpy of the substrates, the substances we have inside. But we also can put in energy by heating, for example, into the system, and we could put in energy by mechanical steering of the system. And this is then the mechanical steering is set as a Ws. And the heat which we put in the system is defined by Q. As in biological systems, if we have a growth in our system, we will produce heat. You will in general need to remove the heat. So therefore, we say that we take the heat out of the system because it fits better to what we usually do. Usually we don't heat the system, we cool the system as soon as we have growth. Of course, if you have a sterilization process and so on, you put in the heat into the system. But this is what you have done in chemical reaction engineering, because heating up things or so and doing the calculation is chemical reaction engineering. Here we are in bioprocess engineering. What we talk in the context of this lecture is, of course, just things where we have growth, and there we will produce heat. Okay, so, and of course we have the law of conservation of energy, that the energy would be put in minus the energy we take out at the end needs to be in sum the energy which accumulates in the system. And it's of course similar to the mass balances. Then we can set up a general form of energy balance and we can simplify it for steady states, for example, and so on. Now in bioprocesses, you remember that also kinetic energy is an energy. So if you with your car drive 250 kilometers per hour and you drive on a wall, then you realize that kinetic energies can be really relevant. However, in bioprocesses, whether your stream is pumped in with you have flow rates, of course, but a speed of 0.2 meters per second or 0.3 meters per second doesn't really matter with respect to the energy. And the same is whether you drop it in from 1 meter or whether you just pump it in from an equal level, doesn't really matter. So of course it's an energy you bring in your system, but compared to the other energies, this is simply neglectable. So we're in engineering. So if the energy coming from such a system is at the level of 0.0 something percent, we don't care, because this our cooling system, for example, what we need to dimension doesn't this is even in the error of the dimensioning of the cooling system, so we don't need to take that into account for the calculation if we have a growth of our biomass. This could be different if we have other processes. Now, a general form of our energy balance in bioprocesses with simple in and output stream looks like this. So it's simply, these equations look so complicated, but it's very easy. So we have here, remember, we have mass flows going in and out. We have our energy flow, our heat flow going out, and our mechanical energy flow going in. So here is our heat. It's minus Q by definition because we say we take it out, plus our mechanical energy, and this is the accumulation term of the energy. And then I have the energy which comes in for each of the mass components. So it's the mass of component 1 which goes in, fold the specific enthalpy of this component 1. And you sum up everything which goes in, and you subtract everything which goes out. So it's math out of your component J plus fold the specific enthalpy of your component J. And this you just simply sum up. You simply need to look up or know the specific enthalpies or the enthalpy differences, as you'll see in a couple of seconds, and then you can calculate what is the change of energy in the system. So that's, of course, general thermodynamics. That's not something which is only valid for bioprocess engineering. If we have a steady state flow process, our delta E gets 0, so we just have this equation. And if it's an adiabatic process, we have no heat transfer from or to the system, so this Q gets 0. We have this equation. Again, this is something you know from thermodynamics. Now, how can I change my enthalpy? So I'm talking about this term now. How can I change my enthalpy? I can change the temperature, then the enthalpy will change. I can change the phase, then the enthalpy will change. So I can make a phase transition from liquid to gas, for example. I can mix or solve, then I can have an enthalpy change, or I can have a reaction and I can have an enthalpy change. So mixing or solving is in bioprocesses also usually neglectable, but of course in chemical processes it's relevant. Simply if, for example, if you put concentrated acetic acid into water and you mix it, then you will produce a substantial amount of heat, but usually you don't go with these highly concentrated solution in bioprocesses because your microorganisms simply will not survive that, and therefore the mixing enthalpy changes are in general neglectable. The same is for solution enthalpy changes. However, the reaction, of course, not. Now, the cool thing, what you know from thermodynamics, is that enthalpy is a state function, so changes of a system do not depend on the path from the start to the end state. And this is, of course, cool if you want to calculate these enthalpy changes. Now, as energy balances concern differences in enthalpy, you need to calculate always relative to a reference stage. And the cool thing is the reference state you define as you want. So you just use the reference state which is most easy for your calculation, as it doesn't matter at what point you define your reference state, because you always look at enthalpy changes. You take the one which minimizes the amount of calculations you have to do. That's very simple. So H equals 0 is assigned arbitrarily to a reference stage, for example to 1 atmosphere 0 degrees. Of course, this absolute enthalpy at this stage is not 0 joule, that's clear. You have not the work, so it's just an assignment. And now you can calculate the enthalpy changes. Of course, you cannot calculate absolute enthalpies. Again, this is what you have learned in thermodynamics. This is what you learned in physical chemistry or in chemical reaction engineering. Nothing new here. It's just to repeat it. And if you then want to calculate, this means that if you want to calculate now an enthalpy change for if you react peroxides to oxygen and water, and you do it at 35 degrees. However, the tabulated values for your reaction heat is at 25 degrees. Then what you do is simply you heat the H2O to you cool down to 25 degrees, calculate the enthalpy change, take the listed enthalpy change for the heat of reaction, and then you heat again up to 35 degrees and then sum everything up, and then you have the enthalpy change of this path. Again, we are in normal thermodynamics, and it doesn't matter how you get there. So what you do in between is not relevant. It's just from here to here, use that path. Now, what about a change in temperature? So if I change the temperature, I have a sensible heat change. It's called sensible heat. So it's the heat transfer to raise or lower the temperature of a material. Now, a sensible heat change is a change in enthalpy of the system due to the variation of the temperature. That's clear. So if I change the temperature of the system, I will have a sensible heat change. How to calculate that is also something you know from physical chemistry or thermodynamics or chemical reaction engineering. You calculate it based on the heat capacity of a given material, and the symbol of the heat capacity is Cp, and this is the SI unit, but of course it can be listed in different ways, so always have a look in how it's listed if you apply it. Cp is a function of temperature, and often you have a polynomial function in your tables as a function of a temperature in order to be able to calculate it. However, in bioprocesses, again, we're not in Frank Platte's 2000 degrees, 20,000 bars things. We are at around about 37 degrees, plus minus a couple of degrees. So in these cases, temperature changes are usually small, and therefore we can, in general, for our purposes, consider Cp as constant, making life easier. Yeah? So maybe I just look back whether I have lost you. No, I didn't have lost you, so you're experts in thermodynamics. That makes me happy. So I go further. Again, this is repeating what you have already had. Now, if you want to calculate delta H, also the enthalpy changeables with respect to sensible heat, if Cp is constant, then you have this equation. Delta H is the mass fold the heat capacity fold the difference in the temperature, and that's it. Okay, and if you have, of course, a variation with the temperature, you need to take that into account. This is a very simple example. I don't want to do the calculation now here because I want to come up with a homework, and this is, as you know, what you have already made. So what is the enthalpy of 150 grams formic acid at 70 degrees and 1 atmosphere relative to 25 degrees and 1 atmosphere? And we have the heat capacity of formic acid at 20 degrees to 100 degrees, so it's constant in this range, and it's tabulated at as 0.524 calories per gram per degree Celsius. So it could be, so it's not Kelvin, it's not Joule, and so on. That's the point. So it's not necessarily tabulated as SI units. So here it's more the conversion of units which is relevant. And we apply this equation 33. Here we are. So this is this one, and simply put in the value. So delta H is mass fold the heat capacity fold the difference of the temperature, and we just put in the value. It's 150 grams. We put in 0.524 calories per gram per degree Celsius, and we put in the temperature difference. It's 70 degrees minus 25 degrees Celsius, and we end up with 3,500 calories, which is 3.5 kilocalories. And of course, if requested, we could convert that to joules. So we just put everything in this formula. This is what you have already done, so therefore we don't need to do that again and again. Now, what about phase changes? Phase changes are things like vaporization, melting, and you know that these phase changes have substantial changes in internal energy or enthalpy. So a phase change in general you cannot really neglect. So in this phase change, the heat which is in this change is called the latent heat. This is the heat transferred to the system, causing a change of the phase at a constant temperature and pressure. So latent heat of vaporization is the heat required to vaporize a liquid, heat of fusion to melt a solid, heat of sublimation to directly vaporize a solid, and the inverse processes correspondingly release the energy and are then simply assigned with a minus. Now, to calculate the enthalpy of a phase change, again, you have usually listed them for boiling points, melting or sublimation points at 1 atmosphere, and then also you go for your path and then can calculate it, and then you can directly, if you come to its temperature where it's listed, you can directly multiply it with a mass, and then you have your change in enthalpy from this latent heat change. How to do it? So before I look at the question, first we have a look how to do it. How to calculate enthalpies of phase changes. Again, you use the path. So let's assume you have a liquid at 30 degrees. This is, for example, your bioprocess. This is your water, for example, and you have always some water lost due to vaporization, and you want to know what energy is required or used by this process. And as it's now, this liquid is not water, obviously, because it's it boils at 60 degrees, so that doesn't matter. So you have then listed for 60 degrees the heat of vaporization. So you then heat it up to 60 degrees, use the tabulated value, just multiplying with your mass, of course, and then you cool it down, and then you have this for this path. So that's very simple. So this is just bringing all these things together, what we need to set up for an energy balance. Now just very brief look whether there are questions. No. So it's cool that your thermodynamics basics is really still there. Now, how do we set up now an energy balance? So it's the same as for a mass balance. The first thing to do is you generate a flow diagram. So it should include all in-outlet streams, composition, and of course you should include now the temperatures of the streams and the energy transfer energies and so on. This needs to be added. State the unit, state the calculation basis, assign the reference state, and state the assumptions. This is the same as for mass balances before. And now let's start with an example. We have an example of a continuous water heater where water at 25 degrees enters an open heating tank at a rate of 10 kilograms per hour. Liquid water leaves the system at a rate of 9 kilograms per hour at 88 degrees. The remaining water is lost from the system through evaporation. A, at steady state, what is the rate of heat input to the system? So it's a heating tank, it's not a reaction. So this is basic, what you have already seen in chemical reaction engineering or in thermodynamics. So this is nothing new, and it's not a kinetics, it's just a balance. So we have no differential equations here, it's just a balance. Yeah. Okay, so for this, of course, you need always these enthalpy changes. You need the heat of vaporization. You need to know this is something which is listed. But of course, also you would expect if it's water, this is all listed for 100 degrees. So this evaporation stuff might be listed for 100 degrees. So we have to then heat it up to with a heat capacity of water to 100 degrees and so on. So you could need to calculate quite a bit around, but the cool thing is for water, as this is so often used in calculations in bioprocess engineering, because it's always aqueous solution, you have for this, you have a so-called steam table. So in this case, enthalpies of saturated water and steams are listed. So you see here we have the temperatures, then the steam pressures and the saturated list, and we have listed all the values. So we have the liquid, the enthalpy for the liquid. We have the heat of the latent heat for the evaporation, and we have then the enthalpy of the vapor. And if you look at 88 degrees, for example, it simply reads that the specific enthalpy here, given in kilojoule per kilogram of your liquid, is of course way lower than the specific enthalpy of your vapor, because the heat of vaporization is in this term. And the cool thing is, if you use this table, you have all values in this table. So you simply can put the values, and you can put this very initial equation what we have, that you simply, this was a bit far away, where you simply put your, here we are. So So you can simply use this equation then, where you simply add up all your streams, subtract all your streams which go out to calculate the enthalpy changes. This makes, of course, life very simple in this case. So I am here. Okay. So here the reference rate is the triple point of water, 0.01 degree, 0.611 kilopascal. So we would use that reference stage because we don't why to use another reference stage. So what to do now? What you do now is assemble the system. So I'm having a look at the watch because I want to come to the homework today. So just I'm just deducing the function of time we have for this exercise. Continuous water heater. Okay. Okay, so we will go quicker with the solution here because I want to come up with a homework. So assemble, analyze, and then do it. So please now, this is really what I ask you to do is please come up with a flow sheet. This is something, please try it yourself. Set a flow sheet for this process that you have a clear idea. So I give you 1 minute for that, and then everything should be fine. Now the minute is gone, and your flow sheet should look like this roundabout. So this comes from your exercise. You have your liquid water coming in with a rate of 10 kilograms per hour and 25 degrees. You have the liquid water going out, 9 kilograms per hour, 88 degrees, and you have your water vapor going out with m kilograms per hour, 88 degrees. So of course the water vapor has the same temperature as the liquid vapor, and heat, you need to put heat into the system. So this is what your equation should look like. This is a minus q in this case because you put it in, and you remember that in our equation by definition we have it in the other direction. So this is your flow sheet, and based on this flow sheet we can start now and do the calculation. So of course, first of all, you start with the assumptions. It must be not leaky and so on. The system must be homogeneous, so inside everything looks the same. The evaporation occurs at 88 degrees. There is no shaft work because we have no shaft work given in this exercise. So you stated there is no shaft work. This is unlikely that there is no stirring, but there is no shaft work. And there are no additional heat losses in the system. That's what we assume. So now it's very simple because the first thing to do usually is you have to solve the mass balance first. Because here we have 10 kilogram getting in, 9 kilogram getting out. Obviously the remaining must be here, but this is already a mass balance. Of course here it's very simple. So not much can be lost here. Of course, for an exam, if we talk about energy balances, it's unlikely that you will have to solve a mass balance first, which takes 5 hours to solve because there will not be much time left for the energy balance. So, well, we just then can use the data from the steam table what we need. So we need the specific enthalpy of the liquid water with respect to our reference stage for 25 degrees. We need the specific enthalpy of liquid water with respect to 88 degrees. And we need the enthalpy of water vapor at 88 degrees. So this is just what we transfer, and then we can do the calculation. So here we go. Okay, so we just copy the values here from the steam table. So we need H liquid H2O 88 degrees Celsius is equal to, we have it from the table, 3 68.5 kilojoule per kilogram. And then we have the H, saturated steam, also 88 degrees, and this is from the table 2656.9 kilojoule per kilogram. And we have the H, liquid water, 25 degrees, and this is 104.8 kilojoule per kilogram. Okay, there is no reaction, and the mass balance is of course then M in is equal to M out, as there is no reaction. And at steady state, we have this equation where we have the sum of our masses flowing in for the specific enthalpy minus the sum of all the masses of all components going out minus the specific enthalpy minus the Q plus the WS is equal to 0. WS is 0. The Q is the thing what we want to calculate, so we can use this equation. And from our system here, we can then take the value. So the inflow is just the liquid water. So we can write down now the energy balance equation like this, that we have the liquid water in, the MH liquid in at 22 degrees minus MH, I make it like this because that's liquid out minus MH vapor out minus Q is equal to 0. So this comes from this general energy balance. 0 at the end because there is no heat accumulated in the system, and the shaft work is 0. So now let's first complete the mass balances very quickly. M liquid in, this is not very nice. M liquid in is equal to M liquid out plus M vapor out, and therefore of course we come in that our M vapor out is 1 kilogram per hour. This is certainly not the most complicated mass balance ever. And now what we need to do is we simply need to put all values. So we put then the mass of our liquid in, which is 10 kilogram, multiply it. So the masses, then we multiply it with the H coming from the liquid in, which is this value, and we multiply the H liquid out, which is this value, and we multiply the H from our vapor out, which is this value. So we just put in these numbers. We put in 10 kilograms here, liquid out is 9 kilograms here, vapor out is 1 kilogram here, and we then put in the corresponding values for the specific enthalpy. And then if we put that everything in, then we get, and we solve this equation to Q here. So we solve to Q. So plus Q is equal to this MH liquid in at 22 degrees minus MH liquid out at, of course, at 88 degrees minus MH liquid out at vapor out at 88 degrees. And then we get, if we put that just the values in, then we get Q is equal to minus 4,925.4 kilojoule per no, it's per hour in this case, I think, but this is okay. So we just keep it at kilojoule, and this value is negative. Therefore, we must bring in the heat by definition. If it would be positive, the heat would go out by definition. That's it for this equation, and this is the solution. So this is what comes out. So I just put in the values here. I didn't write it again. It's because writing it again just takes time. Okay, now just to make sure, oops, can you explain it? Go slower in the next lecture. To take notes or to do calculation if you go at this speed. I'm sorry for that because I want to come to the homework. So that's usually I go slower, but I need to come to the homework. And the good news is that you can, of course, watch this part, what is a bit quicker again. Yeah, so you have the point again. But dude, if I don't come to the homework, we have a real problem because you can't do anything at home. But this will be hard to think about question, and during the live chat is the best moment to ask them. Yeah. Okay. Wait a minute. And of course, you can rewatch the lecture and stop it when you need more time. But then we will always spend at least twice the time the lecture is supposed to. So. Promised. Yeah, in future I will try not to go too fast. Today it's just because I want to reach that point, and we need to reach that point to get to the balances. And if I would go slower, we would have to add half an hour again. And then this is even more. This takes long. And I have an exam afterwards. So this is the reason why in this case it's slower. So Sorry. I know it's fast. Just go for this. I think the first part was slow enough, yeah. But now this part might have been a bit faster. However, remember what we did now in a more speedy way are things that you have already heard in thermodynamics and in chemical reaction engineering. Therefore, I'm feeling still kind of okay, because I didn't kill you with new information. So I try to slow down with the new information. But again, I want to get to the homework. This is something you understood. Then it takes more time. So by the way, I want to thank you that you're all here, because I think that really helps. Because if you just watch these things without doing it yourself, things will not help. Yesterday, I had, I think, just 20 students in applied microbiology, and I said, wow, that's not a lot. And they complained that the information density was not high enough. And then I thought, wow, this complaint I never had in my lectures. Okay, so sorry for the speed. Again, we want to come up to the point, but here it's quite simple. So you just use this equation you had before. A very important point for you is, please make sure that you have your formulary next to you and at the next time, if not at present, a printed out version, because then you can always look up to the formulary. Yeah, and this very simple thing is, we have just put in the values. We have we took the values from the table, put these values in this formula, and that's it. Yeah. Okay. So we come to example 8, and this is the homework, and therefore we wanted to come here. So now we have in the process cooling in downstream processing, and there we have the processing of gluconic acid in a concentrated fermentation broth containing 20% gluconic acid, and this is cooled prior to crystallization. The concentrated broth leaves an evaporator at a rate of 2000 kilograms per hour and must be cooled from 90 degrees to 6 degrees. Cooling is achieved by heat exchange with 2700 kilograms per hour water, initially at 2 degrees. And the question is, if the final temperature of the cooling water is 50 degrees, what is the rate of heat loss from the gluconic acid solution to the surrounding? So the most important thing here is to adequately set up the flow sheet. It's more complicated here because you have two things. You have your coolings, you have your crystallizer, and you have cooling water getting in and getting out. So there are more heat transfers to do. So of course there are always several ways to do that. Now I want to just show you, because this is a homework, remember, the flow sheet. I want to explain you before you start this solving this exercise at home. But make sure that you rethink about the flow sheet and that you redraw that flow sheet on your own, and that you start the calculation with your own flow sheet. Again, you have seen that in the first exercise. The list with the names and the grades is, by the way, uploaded on Moodle, I think. Weil has uploaded it. Well, if it's not Moodle, then just write it in the chat that it's somewhere else. So it's uploaded. So you won't get a reduction of the points if anything goes wrong in your calculation. Of course, if you just have 2 lines, this will be a reduction of points. It's 0.5 points. This is a quite quick thing to do here. So let's talk about, or let's have a look at least at the flow sheet. So again, you have a crystallizer, and you have an evaporation, and you cool it, yeah, and you cool with chilled water. That's a typical thing. So this is now fast, yeah. There's a homework. You do it again. However, what you come up then at the end. So this is how it looks like. So this is your cooler. Then you have an energy which goes to the cooling water. Of course, you have to calculate that, and you have an energy which is lost to the surrounding, and you have your feed stream, and you have a product stream. And the feed stream comes in with 2000 kilograms per hour. It consists of 400 kilograms per hour gluconic acid, 1600 kilograms per hour water, 90 degrees, and your product stream goes out like this, and the heat goes to the cooling water and is lost to the surrounding. And this is what you calculate. This is how you start then your calculation. Please do it at home. Try it at home. It works. So the advantage is that now you have already seen how to set it's not one only way to set up the flow sheet. You could also set up here a separate process for your cooling water, because also your water cooler is then a kind of such a system, but keep it simple. So that's very important. So this is the point here. So again, that's homework, and let's have a look whether there are remaining questions. Why 22 degrees? So this was, I think, the question to the old question. 22 degrees. I think he meant 25 degrees. I'm just having a look whether this was the old exercise. Yeah. Yeah, I meant 25 degrees. Sorry for the 22. So, yeah, 25. Sorry, 25, not 22, 25. Okay, on Moodle, well, okay, that's cool. Yeah, deadline for the homework is simply next week. So it's before the lecture next week. So just put it midnight. Midnight at the day before, because the lecture is at 8, so therefore you should file it the day before. Of course, it's most easiest to do it now after the lecture. Compile everything, have a coffee, and then compile it wherever you are. If you are in Asia, you might already start to have a beer, but digest the lecture a bit, and then start doing the homework in time. Could you explain again what the difference between QI and QW? So of course I can do. So this is in our system here. So usually we had only one heat transfer in this first, let's say, setup of our of our energy balance. We had one heat transfer for our cooler and so on. Here we have two. We have a heat transfer going from this cooler system to our cooling water. Of course, that's intended, and we have a heat transfer which goes to the surrounding. This is of course not something you would how you would set up such a system. Yeah, this is an exercise. So in this case, we have two heat flows, and I just put an index for a W for water, that this heat is the part of the heat going to water, and I put an index as L because this is the part of the heat which is lost. That's the simple difference. It's not an I, it's an L in this case, L for loss. Yeah, how you designate it doesn't matter, but it's just indicating that you have two heat streams here. I think that's the question here. So if there are no more questions, so you will see that the homework is not, it's not like this energy balance, material balance homeworks where you have really to write a lot. This homework can be done easily in half an hour. It's a bit thinking around how to solve it. And if you would know it's right the way, it's 10 minutes. So it's not really a big effort. Okay, so I would say thank you very much for your attention. Thank you very much for your understanding that we needed to come to this homework, knowing that you can, if you have not followed everything, you can scroll back. But remember, the beginning of this energy balance part is all what you have already done in thermodynamics. So this is just bringing that back to the mind. Even that is still thermodynamics. And the next in the next lesson, when we talk about growth in bioprocesses, then we add the real part, our biomass, which is being produced. Yeah, so I just wish you then having a nice weekend. So here in Würzburg we have sun even today, so hopefully you also can enjoy a nice weather. Thanks again very much, and looking forward to seeing you again next week.